Good morning, everyone. Just 2 more weeks to go now, 4 more lectures on the home stretch. Just to remind you where I got to in the last lecture, I'd started on magnetic induction, and I went on to self-induction of a current loop and subsequently a coil, explaining that if you have a changing flux in a circuit, then that will induce an EMF, which then induces a current back in the loop and opposes the current that first caused it. And that's where I got to, and I calculated a self-induction of a long coil. I then gave an example of a load on that, resistive load on that coil, where the EMF was causing a source of voltage in the circuit, and I then went on to the self-induction of a coaxial cable. So I'm going to finish my set of examples here with the self-induction of 2 parallel wires, which this is here the configuration where there's a wire with a current I flowing down here and a current I flowing down there in the other wire, which runs parallel. And these things are separated by a distance d from their centers, and the radius of each wire is a. So that's the configuration. Now, if so what we have to do to calculate the self-inductance, just to remind you, is we have to calculate the magnetic flux in the circuit, and due to a changing current here. Now, because of the geometry of this, right, the field, right, the right-hand screw rule is going around like that in this circuit, and it's going around, it's going around like this in that circuit. So the field, have I done that correctly? It's coming up this way, so I did it, in fact, wrong, didn't I? It's like that. So it's coming up like that, it's going around like that there, and it's going around like that there, and of course the field adds. The field from this wire adds to the field of that, and the flux is the magnetic flux is the field goes through a surface which is parallel to the wires and is in fact radial from the center of this wire here. So this thickness here is dr. This length is the same length as the wires that we're considering. Okay, so that's, sorry, it's a bit of a mess now. But just to illustrate that that section of surface through which we calculate the flux is parallel to the wires like that. Okay, good. So we now have to calculate the self-induction, and this is from Ampere's law. I don't want to, just through time, go through the derivation of this again, but from Ampere's law, outside each wire, the field B is equal to mu naught I over 2 pi r. Right, so where r is just the distance, so that's dr. The r is just the distance to the wire. Right, so this just comes from Ampere's law, the integral round. The loop is the current enclosed times mu naught. Okay, so that's where that comes from. That's the circumference of the loop. Right, so, and the area element, okay, for the magnetic flux is just equal to L dr. Okay, so that's the area dA, and it's parallel to the wire as shown there. So therefore, then I can calculate the magnetic flux. Okay, which is just the integral of B dA. Right, so the magnetic flux is 2, now I'll explain that 2 later, times, right, the integral from A to D minus A, let me write it down first, BL dr. Right, so what's this? This 2 is because there are 2 wires. Okay. Because there is the same contribution from the 2 wires. I hope you can see that the contribution will just be equal from them. So, and the integral is the same from either wire. Okay, so that's the factor of 2. This here, of course, LDR is the area dA, and sorry, I'll call it little a for consistency. B is the field at a distance r from the wire. So this just gives me phi is 2 integral A d minus A, and the integral, of course, goes from the centre of this wire, the first bottom wire, up to it goes from the surface of this wire up to the surface of the other wire. So it goes from radius A on one wire to D minus A on the other. And here's the field, mu naught I over 2 pi L times 1 over R dr. All right, so here is the field from the top there, 2 pi R, mu naught I, L times 1 over R. Right, so I just have to integrate that, and of course I get a logarithm. Mu naught L over pi. The 2's cancel, and log E, log to the base E, D minus A over A times I. The I, of course, is not in the logarithm. Okay, so that's the flux. So we now can get the self-inductance. L is just by definition the magnetic flux divided by the current, which equals mu naught L over pi log E D minus A over A. Right, so that is the self-inductance of 2 parallel wires. And so the self-inductance per unit length is you just take L to the bottom, and if the radius of the wire is very small, compared to the separation, that just becomes that. D minus A over A just becomes D over A. Right, so that's the self-induction of two parallel wires. So all these sorts of things can be asked in prelims. And this is just a summary slide, so you've got it all in one place. I've said all this. I calculated the self-inductance of a long coil. I did a coaxial cable. I did two parallel wires. And the units of self-inductance is the Henry, which is, I don't know why they named a unit, again, with the guy's Christian name, but that was a joke, by the way. Fell very flat. So I think that had everybody in stitches last year, that one. So it's the Henry, and when a current changes at 1 ampere per second, an inductance of 1 Henry results in the generation of 1 volt of potential difference. That's the definition. Right, that's self-inductance, finished self-inductance. We're now coming on to mutual inductance, which is the same sort of thing as self-inductance, but here we have two separate circuits. Right, self-inductance, the EMF was, if you like, a coil or whatever was linking its own flux, providing a back EMF for the current that was causing the change. Here we have two independent circuits where one circuit is providing a changing field which is picked up by the other circuit. Right, so this, in the simplest case, we have two loops of wire. Current I1 in the first loop generates a magnetic field, B1, which penetrates this other loop, circuit 2. So if we have a change in current I1, we'll have a changing magnetic flux through loop 2. And therefore will induce a voltage in the second loop, loop 2. Right. I mean, as an aside, we also generate a self-inductance in the first loop, but I'm just considering now mutual inductance. Right. So define mutual inductance. Inductance. And the symbol is M. M. So, well, right. So we can define it two ways. We can define mutual inductance M. So the first definition, well, it's actually an equivalent definition, is the mutual inductance of in loop or circuit 2 due to a change in circuit 1, which is the flux linked in circuit 2 divided by the current in circuit 1. Okay, remember it's all linear, so I can just as easily write here that this is equal to d phi 2 by di1, which you'll sometimes see it written as well. All right, because it's all proportional, so it can be written either way. So also M12. So here we have, it's going the other way now. So if we have a change in circuit 2, this is the mutual inductance in circuit 1, which is equal to the flux in circuit 1 divided by the current in circuit 2. So this is just equal to the change in flux in 1 due to the change in current in 2. And as an aside, well, not as an aside, it happens, which we could do. I won't derive this, but I'll demonstrate for an example that M12 is equal to M21. So this, if you have a mutual inductance 1 due to 2, that equals the mutual inductance of 2 due to 1. Right. And this here, I just say, this I can write like this because phi is proportional to I. And the thing is that in textbooks you'll see it written like that. At times you'll see it written like that. But because it's all proportional, it can be written either way. Right. Now, so I'm going to now give an example and I'm going to do this 2 ways. I'm going to do 2 coils, which are one coil is inside the other, and the first time I'm going to consider a change of current through circuit 1, i.e. coil 1, the outside coil, and look to see calculate the mutual inductance in coil 2. So I'm going to calculate M21. Right, now I hope you can see that this is it's very obvious that if you change the current in coil 1 and produce a changing flux in coil 2, then all the field or the changing field due to coil 1 is linked in coil 2. Right? It's totally immersed inside it. So now coming to the calculation here. So B1, right, we've got a current through coil 1. So let's see, current I1 in coil 1. So B1 is equal to mu naught N1 over L1 I1. Right. Now this I derive. I don't want to do it again, but remember that I took a Amperian surface that looked like that. This went off to infinity. And this L here is just the length through which these coils, this distance here, that line integral, the current is enclosed n times, all right, in the loop. So this is just the Ampere's law, trivially on that a surface within that coil. Right, and again, I don't want to repeat that derivation, but just so you might remember what I did. All right, so area A2 is the area, this is the area of pickup. I'm calling it pickup of coil 2. Sorry, so I hope that's readable. So all this area here will experience the field and the magnetic flux that is linked. Right. So the flux experienced by coil 2 is equal to phi 2 is N2 A2 B1, right? So the magnetic flux, it's B times area, right? So the area is A2 and the field is B1, which is the field from this external coil 1, times the number of turns that are linked, which is N2. So I can just substitute for B1, mu naught N1 over L1, I1, N2, A2. Right, so we're almost there. So the mutual inductance M21 is equal to phi 2 over I1 is equal to mu naught N1 N2 over L1 A2. So it's just what's written there. So that's it. We've calculated this. We've calculated the mutual inductance of coil 2 in coil 2 due to a change in coil 1. So we can go on to calculate the EMF induced in coil 2 due to a changing current in coil 1. Right. So the EMF by definition is minus d phi 2 by dt. It's the changing magnetic flux. So the phi 2 I derived somewhere up there. So minus due to Lenz's law, N1 over L1, A2, N2, di1 by dt. Sorry if that's a bit crammed up. Right, so that's it. So that's the EMF that you induce due to a changing current in coil 1. So the result is minus M21 di1 by dt. That is just essentially what I've written there. This is M21. di1 by dt is that. So I come up with this. All right. So it looks identical to the equation for self-inductance. Compared to that for self-inductance. So it has exactly the same form, right? So this is for mutual inductance, that's for self-inductance. You don't expect it to have any different form. Okay, now it's maybe a bit, it's sort of, I'm just going to fudge this solution now, because go it the other way is not trivial. So we've got, this is the second case. So I'm not actually going to derive it properly because it's far too complicated. But you can see if you go the other way. So what I'm doing now, I'm creating a field, a changing field due to a changing current in coil 2. This is the inner coil. And I'm looking to see what the mutual inductance is in coil 1. So I'm going the other way. And what I want to derive, which I won't formally derive, but I want to derive M21 is M12. Right, but I won't, because, of course, if I change the flux in coil 2, if I change the field in coil 2 due to a change in current, then the field will permeate beyond the solenoid. It's just, if you've got a solenoid, of course the field lines are going to be well behaved here, but then they're going to come out at the ends, they're going to bend back on each other, etc. All right, so but of course the field will be weaker. So, but what I'm going to do, I'm just going to consider the area where the field is strongest, which is within the coil itself. Now you'll say this is a cheat. You'd be right, but it's what else can I do? Because I'm not going to derive the field due to end effects here. Anyway, so it's just much more complicated to go the other way, because before the field was completely enclosed within the inner coil. But let's go do it anyway. So flux experienced by coil 1 is just phi 1 is equal to N1 primed, A1 primed, B2. So what are these primes? It's like the flux of 1 is the field of B2 times the effective area that the coil 1 experiences. Similarly, this is, I don't know the number of turns, this is the effective number of turns. This is the effective area. B2 is whatever B2 is. So of course I'm going to approximate. There's no way I can calculate that field. I just overlap with the volume where B is the strongest. So I'd neglect stray fields. Neglect all stray fields of B2 outside coil 2. So then this becomes an easy problem. Then A1 prime is just A2, so it's the area of A2. We're just taking that the amount of flux linked is only caused by the inner area, and N1 primed is equal to N1 L2 over L1. So it's the number of it's the number of turns that it experiences just due to the length of N2. So of course there's a factor L2 over L1 here, because that's the ratio of lengths. Right. So and finally, and B2, we just assume it's constant. Mu naught N2 L over L2 times I2. So that's just the standard formula from Ampere's law. So in this case, the mutual inductance can be calculated. I'm just going to put all this together. So it's M12 now is equal to phi 1 over I2. Right, so I'm going to do it on a separate line. So equals N1, I'm just bugging everything in, A2 mu naught N2 over L2 I2 over I2. So I2 is this, that I2 is that I2. This here is the, actually that is the magnetic field B. A2 is the A2 in the formula somewhere up there, and N1 L2 over L1 is just that ratio there, N1 prime. So all right, so we've got all that, and then stuff just cancels out somewhere or other. Sorry, I can't. So I2s obviously cancel, L2s cancel, and this just becomes mu naught N1 N2 over L1 A2. which I think is that. Right, it's the same. Gosh, miracles will happen. M21, yes. So, therefore, for this case, M21 is M12. So, now, again, we didn't do this properly. It's called Newman's theorem. Now, I haven't done the calculation, I don't intend to, but if apparently, if we do the calculation properly, the result would have been exactly the same if we'd have done the detailed integral. Right. And there's the summary of mutual inductance. Right, I won't repeat that, but that's the calculation I did. Good. Well, you can see I'm half a lecture behind, which is a little bit of a worry, but this one is a short one. File, view, full screen. Right, so I'm just going to go on to a transformer, which is just an example of mutual inductance at work on a practical level. I will start off coaxial solenoids sharing the same area. So this is just literally continuing from here. I'm then going to come to inductors in parallel and series, which you'll have seen before anyway in circuit theory. And then I'm going to go on to the transformer. Right. So this is now actually a simpler case than this. The coils share the same area. And from before, I'll just write it down. From before, M21 is M12 is equal to mu naught N1 N2 over L1 A2, which is just, I can just call that M. Right. And of course now A1 is equal to L2. So I'm going to write down the, first of all, L1. This is the self-inductance. N1 squared over, I'll keep the A1 and A2 in there. Mu naught N2 squared A2 over L2. So these are the self-inductance. Right, so those are the formulas for the self-inductance. So if now A1 is A2, so if the areas completely overlap, sorry, here is the, I should have put that on there. Here is the figure, it's the same one I showed before. Here the coils overlap. Right, so I can just write here, the mutual inductance is then equal, okay, it's just a bit of jiggery-pokery. There's the formula for the mutual inductance. Here are the formulas for the self-inductance. And if I stick A1 is equal to A2, then I get this. Square root of L2 over L1 times the square root of L1, L2. Right. So hence, mutual inductance is proportional to the geometric mean of the self-inductances. Whoops. right. That's what geometric mean means, right? It's the square root of the product. And so you can see, if the lengths are the same, then the mutual inductance is just equal to the geometric mean. It's equal to the geometric mean of the two self-inductances. So this is a formula you probably will see. It's only true if the lengths of, so if the areas are the same, if the lengths are the same, then the mutual inductance is given by this. Now this is actually a general, this here, well this assumes the areas are the same, but this is a general expression. M is K L1 L2. So that expression there in general, this is in general. So this is a general expression that the mutual inductance is proportional to the geometric mean, the self-inductances. Of course, if the areas are different, if the lengths are different, then K is going to be different from 1. And it's always going to be less than 1 in general. Because if it were bigger than 1, then you can't get more mutual inductance than the product of the self-inductances themselves. Right? So K is 1. It's called the coefficient of coupling. If the coils are completely linked, then the coefficient would be the coefficient of coupling would be 1. So this is the coefficient of coupling. Okay. So, and of course it depends on the geometry of the mutual interaction of the fields. All right, whether a field due to 1 completely links the area of the second circuit. Right. So have I done that? Yes. Now, next bit, you will have seen this before, so I'll zip over it quickly. So, this is now circuit theory, right? I hope I've drilled it into you that whilst I've done everything from an electromagnetism perspective, coils of wire in circuits, actually, in the inductors, experience exactly the same physical effects that I've been talking about here. They've got self-inductance, they link their own flux, cause a back EMF. So you can stick them in circuits like that. And so what happens if you stick them in circuits? Like if you have 2 of them in series. So the first instant in series with no mutual inductance. I suspect you've done this before. The V that is feeding the circuit, the voltage generator, is just L1 di1 by dt plus L2 di2 by dt. Right, so these are producing a back EMF. So the sign in Faraday's law is gone, right? Because I've implicitly taken out the sign by calling this a back EMF. It acts as a resistance to the flow of current, or the flow of changing current. So this is equal to L1 plus L2 di by dt, right? Because I1 is I2 is I in series. Right. I is I1, 2. So therefore, the total self-inductance is just the sum of the individual self-inductances. Okay, you'll have seen that before. I don't know if you've seen this one though. So let's say they're in series, but some of the flux from this coil links the other coil. So you have mutual inductance as well, and this mutual inductance also acts as an impedance to the flow of current because you produce more back EMF. So the second case is in series with mutual inductance. Sorry, I should have changed my emphasis there. It's two inductors in series, but with mutual inductance between them. All right, so in this case, we have V is equal to L1 plus M di1 by dt plus L2 plus M di2 by dt. All right. And of course, there's no need to say di1, is there? di2 is the same. So this is it. L1 plus L2 plus 2M di by dt. Therefore, the total, I call it L here, but it's the total term that's impeding the change of current. So you add up the inductance and you add up 2 times the mutual inductance. So the total, you can rewrite this as L, the total in di by dt term is L1 and L2 plus twice any mutual inductance between them. All right. So the third case, of course, is in parallel. Again, you've seen this. This is the case here. That's the in parallel one. So I write V is equal to L1 di1 by dt is equal to L2 di2 by dt, and I can, because they're in parallel, the V is the same, where I is equal to I1 plus I2. So this is the current flowing through the circuit. So I'm going to write V is L1. Oh dear, I'm just writing it down again. I'm going to write that di by dt. Sorry, that's what I'm writing, which equals then L di1 by dt plus di2 by dt from here. I've just stuck in I in terms of I1 plus I2, which of course is L V over L1 plus V over L2. Therefore, I can write, taking L to the bottom, therefore the total inductance is equal, or rather 1 over the total inductance is 1 over L1 is 1 over L2. Right, so that's an expression that you'll have seen before for the total inductance of a parallel pair of inductors. Then, of course, it's true for any number. Now, right, I'm not going to do the same thing for mutual inductance. There's no point. It's a bit more. It'll take 10 minutes to do, and it's not incredibly informative. but you can add in mutual inductance as well there. Right. Coming now to the transformer, and there's nothing new in the transformer at all. We've just got two coils. It's sort of a practical application. And I'm sure you all know transformers step up either voltage, well, both voltage and current in a circuit through their mutual interaction. Well, if they step up voltage, they step down current, etc. So they're just used to transform an alternating voltage in one circuit to another by scaling up or down as the application demands. So, and I'm only just repeating now what I've said. You have what's called a primary coil and a secondary coil. So the primary coil creates a flux, which I'm going to call it phi p for primary, is the area of the primary times the field in the primary. And this is per winding. Right, so that's the definition of flux in the primary coil. So that results in an EMF. In the secondary coil. And the EMF is equal to minus d phi s for secondary dt. All right. And this again is per coil, per winding. So every winding of the coil in the primary creates a term for the flux in the secondary per winding in its own right. So we've got to. So that's just sort of obvious. So the coils are coupled. Okay. So the flux in the secondary is the coupling constant times the flux in the primary, where K equals 1 for an ideal transformer. This is just like saying if you've got perfect transformer, perfect linkages, the flux in the first coil is exactly equal to the flux in the second. Right, they're perfectly linked. Right, so this gives, so K depends on geometry. Depends on geometry, coupling, etc. Right. Good. So the ratio of EMFs. EP is equal to minus NP. So this is now the number of turns, d phi p by dt. And the EMF in the secondary is minus NS, d phi s by dt. Right, and this gives, and I'm going from EMFs to voltage now. This gives the voltage in the secondary over the voltage in the primary is d phi s by d phi p times ns over np. So this is this is what I call K, the coupling, and this is just the winding ratio. Okay, so what we've got here is that the voltage induced in the secondary coil due to the voltage, change of voltage in the secondary coil due to a change in voltage in the first coil, the primary coil, is just equal to the ratio of the terms. And so the transformer will step up or step down the voltages depending on the ratio of the turns. So if you have more turns in the primary, then the voltage will step down and vice versa. Right. Good. So that's the voltage. So what about the current? Well, if we assume there's no resistance in the coils, all right, there'll be no resistance in the coils at all, say, then there's no power dissipated, and the power has got to go somewhere. So all the power gets transferred from one coil to the other, just because of the conservation of energy. So the power is VSIS, which I hope you're familiar with. Well, yeah, power is volts times current, right? So the voltage times current in the secondary is equal to the volts times current in the primary, which gives the ratio of currents, which is inversely equal to the voltages, all right, which equals 1 over K NP over NS. All right, so if you step up the voltage through the ratio of turns from the primary to the secondary, you step down the current in the same ratio to maintain the conservation of energy, so that the power in a perfect system is transferred from one to the other. Good. So I actually did all right there. That's just a summary slide, and I'll finish off the next lecture tomorrow with energy stored in an inductor. And then we'll come on to, gosh, I forget. Anyway, we'll come on to something different. Okay.